Hi, this is Mr. Mac. This is the concept video for geometric series, reference number 11.3. Now, first of all, in a geometric sequence, a sub 2 is equal to a sub 1 times r. A sub 3 is equal to a sub 2 times r, but a sub 2 is a sub 1 times r, so we get a sub 1 times r squared. Now a sub 4 is equal to a sub 3 times r. It turns out to be it's equal to a sub 1 times r cubed. And if you look at this pattern that's developing, notice you're not multiplying a sub 1 by r at all. A sub 1 is just a sub 1, but a sub 2 is what you get when you multiply by r one time. A sub 3 is what you get when you multiply by r two times. A sub 4 is what you get when you multiply a sub 1 by r three times. So a sub n would be what you get when you multiply a sub 1 times r n minus 1 times. And this is a formula for the nth term of a geometric sequence, and this is an important one to remember. Now, one of the obvious applications of this is to use this formula to find geometric means. Now, if you were asked, for example, to find, find 3 geometric means between, okay, and let's come up with some numbers here. How about 3 and 48? Now, a geometric means are terms of a sequence that go in between two numbers that form with those two numbers a geometric sequence. So what you're really being asked to do here is to say 3, comma, a number, another number, another number, and then 48 will form a geometric sequence. And we're to look for the 3 numbers that would fit in there. Well, now, the way we do this is we count, first of all, 1, 2, 3, 4, 5. So 48 is a sub 5, and n then will be 5, and a sub 1 is 3. Question is, we do not know what r is. If we knew what r was, we could just multiply 3 by r, we get a sub 2. We'd multiply a sub 2 by r, we get a sub 3, and so forth. But we can use the formula that we just derived. A sub n is equal to a sub 1 times r raised to the n minus 1 to find r. So let's do that. 48 is equal to 3 times r to the 5 minus 1. Now that's r to the 4th. So to solve for r, the first thing we would do is we would divide both sides by 3. And we'd get r to the 4th is equal to 48 divided by 3, and we all know that's 16. Now, the book doesn't actually do this, but we have done this already in the book, and so let's do this mathematically soundly. What we're going to do is we're going to take this equation and solve it for r. Now, that would mean r to the 4th minus 16 is equal to 0. Now, I'm sure you recognize 16 as 2 to the 4th. And r to the 4th minus 2 to the 4th factors as the difference of squares. It becomes r squared plus 2 squared times r squared minus 2 squared. And then, of course, we can solve by setting each of these factors equal to 0. If r squared plus 2 squared, I'm going to write 4 equals 0, r squared equals negative 4, r is equal to plus or minus the square root of negative 4. Remember, when you take the square root of both sides, you've got to introduce a plus or minus sign. So we get r is equal to plus or minus 2i. Or r squared minus 4 equals 0 gives us r squared equals 4. R is equal to plus or minus 2 when we take the square root of both sides. So we actually have 4 different sets of common ratios that we could use. Now, what that means is, and let's just go ahead and write this, we have 2, and then a number, and then another number, and then another number, and then 48. And what we want is to find the geometric means for this. Now, if R is 2, then we would get 2, and 2 times 2, oh, no, I'm sorry. The first number was 3, wasn't it? Okay, so let's do this again. 3, and then a number, and then a number, and then a number, and then 48. Okay, now, turn this into a cloner. So now, if R is 2, then we would have 3. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And 24 times 2 is 48. So 6, 12, and 24 could be the 3 geometric means between 3 and 48. But if R is -2, that would mean that our first number again would be 3. And then 3 times -2 would be -6. -6 times -2 would be +12. Positive 12 times -2 would be -24, and then -2 times -24 would be +48. So that one works as well. So the 3 geometric means could be -6, 12, and -24. But now, if R were 2i, that would mean we'd start with 3 again. Now 3 times 2i is 6i. 6i times 2i is 12i squared, but we know I squared is -1, so we get -12. Now, -12 times 2i is -24i, -24i, and then -24i times 2i would be -48i squared. But since I squared is -1, that would be -48 times -1, which is 48. So 6i, -12, and -24i also work. But now, if R were if R were -2i, that would mean that 3 times -2i would be -6i, and -2i times -6i would be +12i squared. But +12i squared is -12, and then -2i times -12 would be +24i squared. No, I'm sorry. That would be +24i. -12 times -2i would be +24i. But then 24i times -2i would be -48i squared. I squared again being -1, -48 times -1 will give you 48. And so all four of these sets of 3 different geometric means would work. Now, you may say, Mr. Mack, which ones should we use? Well, you have to look at the directions. If it says give 3 positive geometric means between 3 and 48, just the blue ones. If it says give all sets of real geometric means between 3 and 48, it'd be just the first 2 of them. Just the first 2. If it said give all the geometric means between the different sets of geometric means between 3 and 48, actually you should give all 4 pairs, all 4 sets of 3 numbers each. But anyway, that's geometric means, and we use the formula for a sub n to get there. Now, the next thing that comes up is how do we add terms of a geometric series together? If we have let's just come up with a geometric series like 3 plus 6 plus 12 plus 24 plus 48 plus 96. And let's say we wanted to add these terms together. Now, if we tried Gauss's method of turning them around, 96 plus 3 would give us 99, but 48 plus 6 gives us 54. So that method doesn't work. But we know that this would be a sum. Now, what we could do is we could actually take the common ratio and multiply both sides of this equation by the common ratio. 2 times s sub n would be 2 times 3, that's 6, plus 2 times 6, that's 12, plus 2 times 12, that's 24, plus 2 times 24, that's 48, plus 2 times 48, that's 96, plus 2 times 96, that's 192. Now, if we subtracted this second set from the first set, this second equation from the first equation, we would get s sub n minus 2s sub n on the left-hand side. Now, on the right-hand side, we'd have 3, and then 6 minus 6 would be 0, 12 minus 12, 0, etc., 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 minus 192. Now, at this particular point, I'd like to point a couple of things out to you about this equation. So let's get a calligraphic pen here. Let's try, well, I was doing blue, so let's try red here. This 2 here is actually r. Now, this 3 is actually a sub 1, and 192 is really a sub n times r. Now, a sub n is equal to a sub 1 times r to the n minus 1. So if we wanted to, we could think of a sub n times r, just multiply both sides of this equation by r. We get a sub n times r is equal to a sub 1 times r to the n minus 1 times r to the 1, which would be r to the n. So we could think of a sub n times r as a sub 1 times r to the n. So what we end up getting here is s sub n minus r times s sub n is equal to a sub 1 minus, and then I'm going to put a sub 1 times r to the n here. Now, a little bit of mathematical massaging here. We can take an s sub n out of these two terms. We get s sub n times 1 minus r is equal, and we can take an a sub 1 out of both of these terms, a sub 1 times 1 minus r to the n. And so finally, if we divide both sides by 1 minus r, we get the sum of the first n terms of a geometric series is a sub 1 minus, a sub 1 times 1 minus r to the n, how did that happen, over 1 minus r. Well, that was pretty cool, but it wasn't what I was expecting. So let's see if we can just change this all to blue. There we go. All right, so here's the formula for the sum of the first n terms of a geometric series. It's the first term times 1 minus the common ratio raised to the n. Now notice this exponent's inside the parentheses, over 1 minus r. And there's an alternate form, and we kind of just blew by that one. It turns out to be also a sub 1 minus a sub n times r over 1 minus r. I don't think that this formula right here is as useful most of the time, but every once in a while something pops up where they've written a question, especially where that one's really going to be helpful. So you probably should know that one as well. Now, one more thing, we do need to talk about sigma notation when we're dealing with geometric series. Now, geometric series, the expressions that generate them are whatchamacallit, they're exponential in nature. So if we have an indexing variable, k equals 1 to, say, 7, and then let's do 3 times 2 to the k. Now, it turns out that when k is equal to 1, the expression of k, in other words, in this case, 3 times 2 to the 1 is the first term. So, in other words, you just put whatever number you have here in for k in the expression, and that'll give you the first term. Now, the n is equal to 7 in this particular case. K starts at 1, ends at 7, so it's 1, 2, 3, 4, 5, 6, 7. Now, r is the base of the exponent. In this case, it's 2. R is the base of the exponential expression. So you can use the formula for the sum once you know a sub 1, n, and r. Now, one thing I'll mention, I mentioned this back when we were doing sigma notation before. If they don't start with a 1 down here, let's say you have sigma k equals 3 to 9 or something like that, of 5 times 2 to the k minus 3. Then n turns out in this case to be 9 minus 3 plus 1, or 7. Same number here. And notice, if you have 1, 2, 3, 4, 5, and I were to ask you how many numbers are there, you would say, well, there's 5. But if you were to subtract the first number from the last number, you would get 4. Remember, when you're subtracting the first number from the last number, you're really counting how many spaces there are in between the numbers. There's always one more number than there are spaces between them. But if you learn how to read sigma notation so that you can get the first term, the common ratio, and how many terms there are, then you can use the formula for the sum without any trouble. So that takes care of this particular section, and have fun with the exercises. And we're done.